Hello everybody and welcome back. Today we'll be talking about spring forces and how to use differential equations to solve them. So first of all, we'll start with Hooke's law, which is the force of a spring equals negative kx, where x is the displacement and k is a constant that has to deal with the stiffness of the spring. And so we know that force in general equals mass times acceleration, and we also know that acceleration is the second derivative of position with respect to time. So substituting this in, we can say that mass times acceleration, which equals mass times the second derivative of x with respect to t, equals negative k times the position. Rearranging and dividing by mass on both sides, we get the second derivative of x with respect to t plus k over mx equals 0. So this is a second order differential equation that is general to Hooke's law. Now what we can say is that x equals e to the rt. So this is just a way of solving differential equations that are linear. So that just means that it is second order, then first order, then zero order, all the way down. So it follows that pattern. And setting x equal to e to the rt is particularly useful because typically the e to the rt's cancel and you're left with this equation and you solve for r, which gives you the value to put there. So in this case, we need to find the second derivative of x. So we can say first derivative of x equals to r to the ERT, and the second derivative is r squared e to the RT. Now if we substitute this in, we get r squared e to the RT plus k over m e to the RT equals 0. And in this case, we can factor out e to the RT. So e to the RT times r squared plus k over m equals 0. Now, we have something very interesting here because e to the RT can never equal 0. And since it cannot, then we can ignore it for now. So that means that this other term right here needs to equal 0. And so solving it for r, we get r equals plus or minus the square root of negative k over m. Now that's also interesting because that's imaginary. You have a negative under the square root. So we can also say that it's equal to plus or minus I times the square root of k over m. And for simplicity's sake, we're going to set omega equal to the square root of k over m. So this also equals plus or minus I omega. So now, if we substitute it back into our value for x, so x equals e to the plus or minus I omega t. So now what we can say is that x equals to some constant times e to the plus or minus I omega t. Because really when we take the derivative of this whole thing with c, the c doesn't play a role really in what's going on. So we can just say that it's some constant. Now, having the plus or minus in the exponent is not particularly helpful, so we can rewrite it as c1, which is just some constant, e to the I omega t, plus c2, e to the negative I omega t. And so there you have it. This is a general solution that we have for Hooke's law. Now, you might be wondering, is that particularly useful to have an imaginary number in the exponent when solving this? Not really. So there's a step further that we can take in order to reach a cleaner solution. So these are Maclaurin expansions or Taylor series expansions for sine, cosine, and e to the x. So these are approximations up to however many terms you decide to have. So if you, for example, like in this case, you could just choose up to 4, or you could add as many as you want. And it goes on forever following this pattern. And what it allows you to do is create these approximations for sine, cosine, and e to the x. And so some interesting things to notice are that sine, in this case, is the odd values of powers of x over their factorials, because this is over 1 factorial. And same over here with cosine, it's the even powers. This is also, yes, so that's the even powers. And then if we look at e to the x, at first it looks like it's a combination because you have 1x and x squared over 2 factorial. But if you look closer, these terms don't really line up. So it looks like it might be a combination of sine and cosine, but in reality it's not, because these are negative signs, whereas these are positive signs. But what that does mean is that there should be some connection between sine and cosine. But first, let's look at a sine graph. So here we have a regular sine graph. And so what we can do is we can set a tangent line equal to it. So in this case, the tangent line is y equals x. And that's actually the first term in the Maclaurin or Taylor series expansion of sine of x. And if we look around the origin, you can see that it's very accurate. And so that means that for small values of x around 0, it's going to be equal to sine of x. And that's particularly useful because in some equations that are more advanced, we can, for small values of x or small values of theta, switch it out for sine of x or sine of theta is roughly equal to theta. But then we could go a step further. We could add the term, so y equals x, y equals x minus x cubed over 3 factorial. And so this is the graph of that. And as you can see, it's more accurate. It's closer to sine of x. So the more terms we add of the Taylor series expansion for sine of x, the closer to sine of x it gets. And as you can see, the range of values that are very close to the actual value has expanded from the previous one. So we can go a step further. We can add more terms and more terms until we eventually reach the full thing. Now, this is also particularly useful for e to the x. And so as you can see, what we've done here is we've substituted x for ix. And what this means is that when we plug it in, we end up being able to combine terms and change the signs of some terms. So, but this all relies on powers of the imaginary number I. So we have I to the first, just equaling I squared equals -1, I cubed equals -I to the fourth equals 1, and then the pattern repeats. So, for example, you could have I to the fifth, and that would be I. So it goes by patterns of 4, and once it gets back, it just cycles through it again. So what this means is that when we plug in ix to these values, you end up, in this case, I, -1, I, 1. And then if you factor out all the terms that are real, which are these, and all the terms that are imaginary, and then you compare them to the Taylor series expansions for cosine and for sine, you end up being able to say that cosine of x plus I sine of x is equal to e to the ix. So what this means is that when we go back to our value of x equals c1 e to the I omega t plus c2 e to the -I omega t, what this means is that we can rewrite this in terms of cosine and sine, because we know that this value is very similar to e to the ix, except x equals omega t. So when we substitute it in, we get that x equals c1 times cosine of omega t, make that clearer, plus I sine omega t, plus c2 cosine omega t, minus I sine omega t. And then when we simplify it, we get that x equals a combination of constants, which is just equal to another constant, times cosine of omega t, plus I times a constant minus a constant, times sine omega t. And so what this is really saying is that the solution to Hooke's law and the solution to a spring force in which no external influence is acting upon it, there's no friction, there's no air resistance, there's nothing slowing it down or removing energy from the system, you end up with this solution, which is just a combination of cosine waves and sine waves. Thank you all for watching, and I'll see you in the next one.